Hi, and welcome to your Lesson 1, Unit 6, Flip Notes on Momentum and Impulse. The physics you didn't know that you already knew. We like to preface this with saying a lot of it is common sense, but we also want to understand the rationale behind these quote-unquote common sense topics. Your definition of momentum is as follows. Momentum has the symbol lowercase p, and it's defined as a measure of inertial energy possessed by a moving mass. Remember, inertia from Newton's first law of motion states that an object at rest wants to stay at rest, an object in motion wants to continue in motion, unless an outside force changes that. When we look at the unit for momentum, it's down here at the bottom, composed of the unit for mass and the unit for velocity. We pronounce that kilogram meter per second. And the formula comes from multiplying together mass in kilograms times velocity. Our first check for understanding is to demonstrate that bigger objects like this bowling ball do not always have a greater momentum. If you were to do the actual numbers on the bowling ball's momentum, you would find that the mass 7 times the velocity 2 gives you a momentum of 14. But over here, a much smaller object, the tennis ball, moving at a considerably faster velocity, multiplied together still give you the same amount of momentum, 14. So always remember, it's possible for a tiny object like a bullet to have the same momentum as a larger object, like maybe a train. It has to do with the velocity. Your second example would be, if we imagine that John is riding a skateboard at full speed, we want to figure out which object has the greater momentum. Your options are John, the skateboard, or would they be equal? When thinking about momentum, we have to consider mass and velocity. Since they're both moving at the same velocity together, riding as a unit, then the object with the greater mass would then therefore have the greater momentum. Answer is John. Take a moment to look at example number 3. And notice that in the end question, it's asking for the difference in momentum between the two. When we say difference, it means to subtract. So we'll go ahead and find the momentum of this first object by doing our mass times velocity, and you get 300 kilograms meters per second. When you find the momentum of this second object, mass times velocity, you end up with the same momentum. So obviously our answer would be that there is no difference in momentum. Go ahead and flip your page on your note helper, and let's continue with our next definition for change in momentum. The symbol would be delta, meaning change, as we've seen before, followed by the lowercase p for momentum. Definition is, it's the rate of change in momentum for an object with varying velocity. Fill into the 4th column that the unit of measurement for change in momentum would also be, if you can follow my mouse, kilograms meters per second, just like momentum is. And this time the equation is what we have circled. Delta P, change in momentum, is equal to mass times the change in velocity. Another way to write change in velocity, we can spread that out and copy that into the equation box on this line, is that delta P is equal to mass times, parentheses, final velocity minus initial velocity, close parentheses. Just to remind you that when you do change in anything, it's always final minus initial in physics. This is going to be crucial on your practice for Monday, so make sure you know how to find the change in velocity. Final first, subtract it from that, the initial. Our last thing that we want to put in the box for change in momentum is that it is directly proportional to the force applied. More force, greater change in momentum. Apply a lesser force, you get a lesser change in momentum. Last but not least, you have the term impulse, symbolized with capital letter I. Definition for impulse is it's a measure of what is needed to cause a change in the momentum of a moving object. Whenever we want to equate impulse to change in momentum, they're always going to be equal to each other. In order to find the impulse necessary, you would consider the force that needs to be applied over what period of time. The unit for impulse is Newton seconds, which came from multiplying force in newtons, and change in time, which would be in seconds. And your equation is here, capital letter I equals F delta T. So your big connection is that impulse is equal to the change in momentum. So if we set these two equations to each other and simplify, we come up with the short version, I equals delta P. But the more useful version is this. If we can just fill in the impulse definition, F delta T, and set it equal to the change in momentum definition, M delta V, that's our more useful form of the equation. Now for some application. When you did your egg projects a couple of 6 weeks ago, understanding momentum and impulse would have been really helpful to you. The key in understanding the answer to this question has to do with this equation here. Your change in momentum will not vary if you're dropping it on the tile or if you're dropping it on the pillow. The mass of the egg is still going to be what it is. The change in velocity will go from the high speed that it's traveling at to the zero when it makes impact. But your key is in this side of the equation. In order to lessen the force, you have to do something to manipulate the change in time that it elapses as the egg is making the impact with either the floor or the pillow. So here's what happens. Yes, in both cases, mass and delta V are the same as stated before. But if we can somehow extend the amount of time that it takes for that egg to make impact, you can have that egg encounter less of a force in which it's less likely to break. So how did you get the time to extend just a bit, enough to decrease the force so the egg wouldn't break? You started to use materials that were elastic, stretchy, cushiony, so that when upon impact, time was extended as the object started to deform or squish or change its shape, and that slight increase in time helped your force to decrease so that you could equal the same change in momentum, just encountering less force. Take a moment and make sure that you're able to justify that answer and fill in a good explanation on your notes, and then let's go on. To maximize the force, in certain times you do want to maximize the amount of force that happens. So unlike with the egg project, here are some examples in which you would need to maximize the force. When you think of certain sports like baseball, if you want to maximize the force, you want to do that with quick, sharp movements like bunting. In karate, whenever you have your kicks and your punches, you always want them to be really quick and short so that the force is maximized with that shortened amount of time. And last but not least, boxing, jabs are always very short and quick so that the force is maximized. If you wanted to minimize the force, like with the egg example, and we'll give some more, you would need to extend the time, apply the force for a longer amount of time. So here are some things that could help you extend the force. When you have padding on walls, again, the deformation and the changing shape of that padding helps extend the time over which the impulse occurs, which allows you to encounter less of a force. With bungee jumping, of course, when that person is snapped back up, you want it to happen over a longer time so that they don't encounter a greater force and have the possibility of injuring themselves. So that elasticity and stretchiness of the bungee cord helps to extend the time so that you incur less force. And airbags totally help to decrease the amount of force. Again, we don't want to lead you to believe that it's taking the force away altogether, but it does decrease the force a considerable amount. Seat belts, they help to extend the amount of force, decrease the amount of force by extending the time. Okay, I'm going to put this video clip up, and this is your prompt to hop on over to your folder on the hub and watch this video clip. There's going to be some questions on it in the future, so take about, I think it's 6 minutes to watch the clip, and then we'll return back to these notes. Okay, to sum that up, how does the helmet reduce the force on the head? It's all about time. When you can extend the time that the helmet is going to have to change shape, to compress, you encounter less force on the head itself. A less traumatic injury, certainly, when the force is decreased. That brings us to the end of our flip notes. Just showing you a couple more safety devices used in sports, all about increasing the time involved in impulse so that you can encounter less force. Thank you, and we'll see you on Monday ready to do some practice and application.